When casting metal, jobbing moulding is ideal where small numbers of components are required at minimum cost. One half of the pattern is placed face down in a box, which forms the bottom half of the mould and is called a drag. Green sand, which consists of sand plus 2 to 3% clay and water, is sifted over the pattern and then pressed around it so as to obtain good shape definition. More sand is added and is compacted with a peg rammer, spiralling from the outside towards the centre of the drag. The last compaction of the sand in the drag is carried out using a flat rammer. The excess sand is struck off and the drag turned over, revealing the pattern and mould joint face. Talcum powder, which acts as a parting agent, is dusted onto the surface. The top half of the pattern is added. The pattern for the riser and for the tapered down sprue are positioned on the drag, and the runner, a groove which allows the metal to flow between them, is marked in. The riser will also act as a head to feed the casting and as a swirl gate to clean the metal before it enters the mould. The top box, called a cope, is placed on top of the drag. The riser and down sprue are replaced. As before, fine sand is pressed around the pattern and the cope is rammed up. The top is struck off. A pouring basin is cut into the sand so as to ensure a smooth flow of metal into the down sprue. A smooth metal flow is important in obtaining a clean casting. The cope is wrapped and removed from the drag. An end-gate is cut from the riser into the pattern. In the other half of the mould, the cope, the runner between the down sprue and the riser is cut in. The half patterns in the cope and in the drag are wrapped and carefully removed. A core is placed in the cavity left by the pattern and forms the hole that is present in the final casting. The cope and drag are reassembled. Molten aluminium is poured carefully into the down sprue. The metal spins as it fills the riser. The metal is allowed to cool and solidify. One of the big advantages of green sand moulding is that the sand can be recycled, and the process is essentially pollution-free. With coal box moulding, the moulds are made up in the same way as green sand moulds, but instead of using clay as a binder, a sodium silicate resin is blended with the sand. This resin sets when CO2 gas is blown through the sand. This process can be carried out quickly, requires less moulding skills, and produces a strong mould. CO2 gas is used in conjunction with a furane binder for the making of moulds, and in this case, cores. The core box is filled with resin-coated sand, gashed with SO2, and then purged with air for 2 minutes. A strong core is rapidly produced. A special coating may be painted onto the core surface to improve the surface finish of the casting or to cause temperature gradients in the mould that will help with solidification and help ensure a sound casting. The use of linseed oil, clay and water to form a binder for the sand has been used for many years, particularly in the production of cores. All the ingredients are blended together until the correct consistency is reached. The sand is rammed up in the core box, knocked out, and then baked at 300 degrees Celsius for 3 to 4 hours. The advantage of this oil sand binder is that it is relatively cheap, but it has been largely replaced by modern resins. Different sands can have markedly different strengths and thermal capacities. It is very important to use the correct sand with the appropriate binder for a given application. This casting is required on a just-in-time basis, that is, small batches of 5 or 6 units on an ongoing program. A cold box process is selected for this application. The binder used is of the self-setting type, lubricating and assisting the sand particles so that they flow into and around the complexities of this pattern. Once the resin has hardened, the mould and pattern is turned over so that the pattern can be stripped off the mould. A mould coat is sprayed on to improve the surface finish of the casting. The cope and drag are carefully assembled. A pouring basin is glued onto the cope. The molten aluminium is chemically degassed just prior to pouring. The liquid metal will try to force the cope and drag apart. To overcome this, weights are added to the cope. A perfect casting. Small numbers of this type of very large casting are manufactured by the pit moulding method. To make this type of casting, the first step is to remove the rubble from the previous casting. Approximately 50 tonne of sand will be used in producing a 40-tonne casting. Self-setting phenolic resin bonded sand is swept to shape, first using the outer end of the strickle board. To help the solidification process, chills in the form of cast iron blocks are laid down in the form of an outer ring. More sand is added, and this is swept to the final shape of the drag. Next, a layer of loose sand is applied. Over this, a layer of cold setting sand is swept to the shape of the top of the mould. The strickle board and the central column are removed. A large steel frame filled with bonded sand forms the cope and is lifted off the pattern. This pattern of the casting is broken up and removed, and is the cavity into which molten metal will run. A mould coat is painted onto the drag. Core and down sprues have been added, and the cope is very carefully replaced. A defective casting of this size is a very expensive item. Cast iron and steel scrap are loaded into the induction furnace. A sample of the melt is taken for computer-aided chemical analysis. You have to get your metallurgy right if you are to produce quality castings. When composition and temperature are correct, the ladle is filled. Slag is raked off. Magnesium and inoculants are added. These will cause the carbon in the melt to form little spheres, thus producing a ductile iron, a material that is much stronger and tougher than grey cast iron. 75% of all castings produced in this foundry are ductile irons. 48 tonne of metal will be poured to produce a 40-tonne casting. The additional 8 tonne will form heads and risers. This metal is not wasted, but will be cut up and recycled. When a small number of metal components are required, a process called rapid prototyping can be used. This involves producing a wax pattern for each component. A computer-generated three-dimensional shape of the component is sliced into thin layers to determine the path of the computer-controlled extruder that will build up the final shape. This wax model takes approximately 2 hours to complete, and when completed, It will be used as the wax pattern for an investment casting. Investment casting is a process whereby the wax pattern is encased in a ceramic shell, the wax melted out, and the cavity thus formed is refilled with molten metal. For very complex shapes or small batch sizes, the waxes will be produced in a manually loaded wax injection machine. The wax is injected into the die. It cools and solidifies. The die is removed, split open, the 18 movable parts of the die slid back, allowing the wax shape to be removed. This is the precise shape of the final product. These cutter bodies are required in large numbers, and so the wax injection process is automated. The waxes are ejected, the die closes and the cycle recommences. The sets of waxes are carefully checked and trimmed and then assembled on a tree. The segments are welded together, thus forming a runner system. The waxes are first coated with a very fine investment to give good surface detail. It is subsequently built up with 10 layers of zircon sand using a silica binder. The investment process is unnatural for automation. Wax is melted out of the shell in an autoclave at 150 degrees Celsius. Any remaining wax is burnt out in a furnace at 750 degrees. The temperature is then raised to 1000 degrees just prior to pouring. The components are broken out of the shell and ground to size. This partially automated linisher has improved productivity by 700% and has eliminated rejects due to over-grinding. Grey cast iron is easily cast, has good machinability and excellent dampening properties, and is inexpensive. A good quality grey cast iron would have a tensile strength of 250 megapascals. A ductile iron will have a tensile strength of 500 megapascals, a strong, tough material. These tensile strengths can be further improved to between 850 and 1600 megapascals by careful isothermal heat treatment, thereby greatly improving the value of the casting. By plotting time versus temperature and noting the change in the metal structure, an isothermal curve for ductile iron is produced. By then adding 2.5 hours to the start of this curve, the complete isothermal heat treatment can be shown. The ductile iron is heated to B and allowed to soak at this temperature to time C. This causes the iron to change its atomic structure into austenite. The iron is then rapidly quenched into a salt bath to temperature D. It is held at this temperature for some hours, point E. This isothermal heat treatment causes some of the austenite to transform into a acicular ferrite. The components are then cooled to room temperature F. Aus-tempered ductile irons have outstanding tensile and yield strengths, good ductility, high impact and wear strength, are 10% lighter than steel, and are ideal for highly stressed components such as these damper plungers. This process is increasingly being used in the automotive industry for drivetrain components. A low-volume process like investment casting can become medium volume by automating the process. So it is with green sand moulding. By incorporating a jolt and squeeze sequence into the mould making process, the mould production time is greatly reduced and handling is made much easier when the movement of the cope and drag are mechanised. The cold box moulding process can also be automated so as to increase productivity. The resin bonded sand is blown into the mould. It is then gassed, and in approximately 3 minutes it is set. These moulds may be designed such that they can be stacked, thus enabling them to be filled together. Hot box moulding is where a thermosetting resin is incorporated with the sand and is set off by heat. The process requires a production run of some thousands due to the high setting up costs, $5,000 for a pattern plate. The heated steel pattern has the resin-coated sand dumped on it. When the resin-sand mixture is in contact with the hot plate, it sets off. The excess sand is dropped away. The curing of the shell biscuit is completed by a heater box. The shell, which contains both the cope and the drag, is removed. Broken in half, and the two halves glued together so as to form the complete mould. The process is quick, gives good surface definition, is typically used in the production of tap fittings, but more often used in the production of cores. The sand is generally not recycled, and the process is being overtaken by the cold box process. The cost of a pattern for the cold box process is $1,000. However, it is a slower process than the hot box and uses more sand per mould. The cost of the sand for a cold box mould would be $6 compared with $2 for a green sand mould. But a higher moulding skill is required for green sand moulding. Many factors must be taken into account when comparing the economics of one moulding process with another. The lost foam process is similar to investment casting, being able to produce complex shapes with high accuracy and excellent surface definition. It is ideal for very high volume production, as in the automotive industry. It is at its very best when components are specifically designed to take advantage of the process. The pre-expanded polystyrene bead is blown into the die and heated to 100 degrees Celsius, causing the bead to expand to its final size. The process requires a dense foam for good surface definition, but not so dense as to produce so much gas that it would have difficulty escaping from the mould. Some of the runner system can be included in the foam pattern, and the foam components can be designed so that they clip together to make more complex shapes. The foam is coated with a refractory slurry. The cluster of components is showered with dry, fine sand, which will produce the outside shape and the inside cavities, generally eliminating the need for cores. All the sand is recycled. Vibration compaction causes the sand to flow into the exact shape of the foam. Pouring basins are added. The plastic sheet forms an airtight seal over the box, to which a vacuum is applied, compacting the sand and aiding in the removal of gases. The moulds are poured and perfect castings are produced. For very high production rates, over 220 moulds per hour, each containing 2 engine blocks, the traditional method of making cores for these moulds was the hot box method. With this process, each operator effectively produced 14 units each per hour each assembled from 12 separate parts. But with a modern core box method of core making, the output per operator is 40 units per hour, assembled from 5 separate parts. These parts are keyed together using a cold setting sand. At the same time as the cores are being made, green sand drags are being produced by a fully automated jolt and squeeze method of production. The drag is sprayed with a mould dressing. The cores are assembled and placed in the drag by a team of 7 people working in unison. The cope is closed with the drag. The launder, which is a type of trough, tops up the pouring furnace that moves along with each mould as it fills them with molten cast iron. The launder itself is periodically refilled from a ladle. The cylinder blocks, when cool, are knocked out and the green sand recycled. A very efficient process. The Hunter process is a fully automated, flaskless green sand mould making process, ideal for the rapid production of castings where some hundreds to many thousands are required. At the heart of the process is a double-sided pattern plate. One side makes the shape in the cope, and the other side the shape in the drag. The machine is divided into 2 halves. The left-hand side makes the drag, and the right-hand side the cope. The drag box is tipped upside down and filled with moulding sand, tipped back again and moved across to the right-hand side, where it moves up and the cope is made using the other side of the pattern. The cope and the drag are compressed at the same time. The cope and drag are separated, allowing the pattern and its box to return to the left-hand side of the machine, where it restarts the process. The cope and drag are united and are pushed out onto a conveyor where the mould is filled with molten metal. There is no container for the cope and drag, that is, there are no flasks. The compressed green sand has sufficient strength to contain the molten metal. The moulds are poured in batches. It is a very economic process for medium to high production runs. The metal is allowed to cool, and at the end of the line, the castings are knocked out. The diesematic method of forming green sand moulds is very fast, 1 every 10 seconds. The limiting factor in the rate at which castings can be produced is the speed at which the metal can be poured into the mould. The mould is made by compressing the green sand between 2 patterns at very high pressure, effectively producing a cope and drag on either side of a block of sand. These blocks of sand combine to form complete moulds which are filled with molten metal. The metal is allowed to cool and the castings knocked out. The sand is then recycled. Cores can be added to the moulds via a carrier that slides into the machine and places the cores into the mould cavity. In this run, 6 cores are being added. These moulds are being poured at the rate of 1 every 10 seconds. There are 6 castings in each mould, so that it takes 1.5 seconds to produce each unit, an incredibly fast production rate. The castings cool and are knocked out. The disadvantage of the diesematic process is in the capital cost of the machine and the ongoing costs of the patterns. To recover these costs, very large orders from thousands to preferably millions of components are needed. This is the case with these railway fittings that are being vigorously exported onto the world market. These cast iron engine blocks have fins that could be damaged during a normal knockout process. To overcome this, T-pieces are added to the mould so that they will become part of the runner system when the mould is poured. These T's are then lifted by hooks, thus removing the castings from the sand. Some of the excess sand is hammered off. The castings are then shot blasted to remove the remaining sand and improve surface finish. The runners and risers are simply knocked off. Whether you are working with very large numbers of components or with very few, the most appropriate method of casting must be selected, and this decision is not a simple matter.